Okay, in 7, Part C, we're told that the hydrofluoric acid reacts with hydroxide ions to yield water and the F minus, the fluoride ion. But really what we're told is that we're going to add 0.4 molar of sodium hydroxide. So I'm just going to write down what's given. We add 0.4 molar of sodium hydroxide, 15 milliliters of it. And it's added to 25 milliliters of 0.4 molar of the hydrofluoric acid. And then we're asked to assume that all volumes are additive. Part C says calculate the number of moles of HF remaining in the solution. Calculate the molar concentration in the solution and calculate the pH of the solution. So the first thing is this is a neutralization. Notice this is a one-directional arrow. So this is a limiting reactant problem. We're given the amounts of 2 of the reactants, and the only reason that I rewrote it, this sodium hydroxide is going to immediately split into sodium ions and hydroxide ions. So these two reactions are the same, but you're given it in terms of sodium hydroxide. So we can figure out the number of moles of both of these, and we'll see which one has more. And we find that we have added 0.006 moles of sodium hydroxide, but we have 0.010 moles of hydrofluoric acid. So since we have more of the hydrofluoric acid, we're basically going to use up, it's a 1-to-1, 0.006 moles of the hydrofluoric acid. We're going to neutralize it. And so then what's left is 0.004 moles of HF. We've used all of the hydroxides, and we've made 0.006 moles, right? So I'll put this down here. We've made 0.006 moles of H2O, and we've made 0.006 moles of NaF. This is what we did when we did basic stoichiometry problems at the beginning of the year. So that's the neutralization part of this reaction. Now, the question says, how many moles of HF will remain in the solution? So we now need to go back, and this number of moles of HF is not going to remain in the solution because now we're going to go back to the equilibrium and say that HF in water is going to create H3O plus ions plus F minus ions. And now we have a starting concentration of 0.004 moles, but we should put this into concentrations. So it's 0.004 moles, I'm sorry. So this is going to be an initial concentration of 0.004 moles, but now we're in a total of 40 milliliters, so 0.04 liters. That's our initial concentration of HF. And our initial concentration of F minus ions is going to come from this. We have this common ion now that's sitting in there before we try to dissociate, and we're going to have 0.006 moles of the F minus in the 40 milliliters, the 0.04 liters. So that's my initial conditions of my ice table, and I'm going to bring that to the next page and start there. Okay, so just copying the concentrations, the 0.1 molar, this was from the 0.004 over 0.04, and this one here was from the 0.006 over 0.04 liters. So just so you know where these numbers came from. So those are our initial concentrations. We have to hit equilibrium again. So now, since there's no H3O pluses right now in the solution, we know that we need to go right, and we're going to lose some of that. So we're going to have 0.1 minus x on this side, and we're going to have x, and we're going to have 0.15 plus x. Now, the K, which you know was given, the K acid for this is going to be the concentration of H3O plus times the concentration of F minus over the concentration of HF. And that's going to be equal to x times 0.15, 0.15, over 0.1, because we're going to use our approximation. And so we can find x. And x comes out to be 4.8 times 10 to the minus 4 molarity. Okay, so now to answer the question, it says calculate the number of moles remaining in the solution. So we're going to go back here at equilibrium. The number of moles remaining in the solution of HF is going to equal 0.1 molar minus 4.8 times 10 to the minus 4 molar. And so this is going to not affect the significant figures. So it's going to be 0.1 molar, which if we multiply that by our 40 milliliters is going to give us 0.004 moles. Likewise, the F minus ions in the solution is going to be 0.15 molar minus the 4.8 times 10 to the minus 4, which is insignificant for sig figs. So we're going to have 0.15 molar, times it by the 40 milliliters. That's going to give us 0.006 moles. So the change for the equilibrium doesn't affect those concentrations because it's so small. However, then it says calculate the pH, and we know that the concentration of the hydronium ions comes out to be 4.8 times 10 to the minus 4 molar. And so the pH, which is the negative log of that concentration, we can calculate that, and that will be the answer to this problem. 3.3 is the correct pH. This level of difficulty would be the hardest level of difficulty at this point that I would expect you to be able to do on an exam. This would be the hardest. But this is this common ion effect you saw in the KSP problems as well. When there's a salt already in the beaker and you're trying to dissolve a salt that has a common ion, you have to start with this initial situation in your beaker. Oh, lastly, one correction, that remember 2 sig figs in our concentration means 2 decimals, and so we need to go over to 3.32 for our pH. Okay, for this problem you're asked to write the equilibrium constant expression for the given equation, so we should be very good at that now. It's going to be the concentration of the silver plus ion squared times the concentration of the CrO4 ion. And then for part B, it says calculate the concentration in moles per liter in a saturated solution of Ag2CrO4. So that's the molar solubility. So here's the answer to part A. That's the expression that we're looking for. For part B, we know we're going to need to have some quantities. So if we start off with none of these, we're going to add x. Actually, we're going to add 2x to that one and x to this because of that 2. And at equilibrium, we're going to have x and 2x of this, and we will have subtracted x moles of that. So for part B, we're going to say that 2x squared times x has to equal our KSP, 2.6 times 10 to the minus 12. So we get 4x cubed equals 2.6 times 10 to the minus 12. And you get x is equal to 8.7 times 10 to the minus 5 molarity. And then we're asked, okay, if that is the concentration of silver ions, that's the concentration of the chromium ions. So the concentration of the silver ions in a saturated solution would be twice that, which would be 1.7 times 10 to the minus 4 concentration. Now, this amount is going to be the maximum amount of molarity that you can make dissolving the silver chromate. So for part C, it says what mass can you dissolve in 100 milliliters. So we know that that's the maximum number of moles per liter that would dissolve. And if we times that by 0.10 liters, the 100 milliliters, we're going to get 8.7 times 10 to the minus 6 moles will dissolve in 100 milliliters. And then we have to multiply that by the molar mass of silver chromate, which is 331.7 grams per mole. And when you multiply that, you get 0.0029 grams. So it's not going to squeeze in here very well. 0.0029 grams will dissolve in 100 milliliters for the silver chromate. Okay, for part D, it says a 0.1 mole sample of solid silver nitrate, well, it's a nitrate, so it dissociates, is added to 1 liter of silver chromate. So let's go back up to our equation up the top here. Right, and we're going to look at this equation. If we add silver nitrate, that's going to cause the silver ions in the solution to go up. Le Chatelier's principle says if the silver ions go up, then this is going to shift in a way that the silver ions need to go back down. If the silver ions need to go back down, we have to make more of the solid. We have to go to the left. We have to shift left. So to answer question D, assuming no volume change, does the chromate ion concentration increase, decrease, or remain the same? If we're shifting left, then both of our products have to go down. So the answer to part D is that the chromate ions will go down. It will decrease. Okay, for the next part, E, F, and G, we're asked about silver phosphate, and the first thing it asks is it gives a KSP, or it doesn't give a KSP, it gives a KSP expression, and it asks to write the balanced equation for dissolving this solid in water. So we're going to make this a solid, and we're going to say that it's going to make 3 silver ions, and it's going to make 1, and we'll put aqueous, and it's going to make 1 phosphate ion. So it's important that you put the charges on these because that's what's happening, and we're going to say aqueous on that. And then it says calculate the value of the KSP. So it says that it's found to have 5.3 times 10 to the minus 5 molarity of this. Now we know that that's a plus 3x, wherein this would be a plus x if we started with none. So our ice table would look like that. So we need to divide the 5.3 divided by 3, and we're going to find that we would make 1.8 times 10 to the minus 5 of the phosphates. And now we can calculate the KSP, because the KSP is going to be the concentration of silver cubed times the concentration of phosphate raised to the 1. So we're going to say 5.3 times 10 to the minus 5, and we have to cube that and times that by 1.8 times 10 to the minus 5, and you'll get a KSP value of 2.7 times 10 to the minus 18. And then for part F, that's part F, and then for part G, it says a 1 liter sample of silver phosphate solution is allowed to evaporate at 25 degrees to a final volume of 500 milliliters. What is the concentration of silver in the solution? Justify your answer. Okay, so the concentration is the molarity. So as we allow this reaction, okay, so we have a beaker, and we know that if we try to dissolve in 1 liter, that we're going to get a molarity of 5.3 times 10 to the minus 5 molar of silver, and that's what was told to us. Now, if we allow this to evaporate, what's happening is this concentration starts to go up, and as the concentration goes up, it will start to precipitate out because it will no longer be at equilibrium, right? If we look at Le Chatelier's principle, let's look up at the reaction again. If we evaporate it, this goes up. If that goes up, then Le Chatelier's principle says we've got to shift left. These got to go down, we've got to shift left, we're going to make more solid. And that's going to keep happening, and as that happens, it doesn't matter how much solid we make, these are going to be our equilibrium concentrations. So the concentration of the silver is going to stay the same. The mass of the silver that's in the solution will drop because you have less solution, but the concentration should stay the same. We're going to start the 2006 problem. We have a saturated solution of PBI solid is distilled, and the concentration of Pb2 plus in the saturated solution is found to be 1.3 times 10 to the minus 3 molar. So we have PBI2 solid is going to be in equilibrium with Pb2 plus aqueous plus 2I minus aqueous So if we start with none, we're going to add x, we're going to add 2x, and we find that the PB is 1.3 times 10 to the minus 3 molar, which means that the I has to be twice that, 2.6 times 10 to the minus 3 molar. And part 1 says write the equilibrium constant expression, so KSP is going to equal PB 2 plus concentration times I minus squared. That's part I. Part double I is going to be calculate the molar concentration of I in the solution. We just did that. 2.6 times 10 to the minus 3 molarity is equal to the concentration of I in the solution. Triple three says calculate KSP, so you can put in KSP equals 1.3 times 10 to the minus 3 times 2.6 times 10 to the minus 3 squared, and you get 8.8 times 10 to the minus 9. That's the KSP. Okay, part B says a saturated solution is prepared by adding PBI to 2 liters. What are the molar concentrations of PB2 plus and I minus? And if we, these numbers, these are moles per liter, and so the concentrations would be the same. So for part B, the concentration of the PB is still going to be 1.3 times 10 to the minus 3 molar, and the concentration of I minus is still going to be 2.6 times 10 to the minus 3 molar. And the justification is that these are concentrations. If we change the volume, we change the amount that we need, but the concentration would stay the same to maintain the equilibrium constant that would be KSP. We need these concentrations to remain the same as long as we were starting with no ions in the solution before the reaction. Okay, so the next part adds a common ion. We add some sodium iodide into the solution. We don't change the volume. And it asks, will the concentration of PB, would this go up or down, this concentration? This should be a B, by the way. Okay, so we add some sodium iodide. That means that I'm going to increase the iodide ion in the beaker. If I increase the iodide ion, then Le Chatelier's principle says, then in order to maintain equilibrium, I'm going to have to decrease these and shift left. So that means that the PB2 plus is going to decrease. So the answer to C is decrease. By adding iodide ions into the beaker, you've offset the equilibrium. You're no longer at K. Your Q value is too big. So by increasing the iodide ions, Le Chatelier's principle calls for a decrease shift. So we're going to decrease both of these products and shift left. Okay, the given information in this problem is that we have 8.2 times 10 to the negative 6 molar, 500 milliliters of barium nitrate. So I'm going to just calculate, so the question says, assuming the volumes are additive, calculate the molar concentration of barium 2 plus and chromate in the 1 liter of solution. So basically, these are half and half. So when I do the dilution, my 8.2 times 10 to the minus 6 molarity times 500 milliliters over my final volume of 1,000 milliliters, I just reduced my concentration in half. It's adding twice as much water to my lemonade picture, right? So that's my new concentration. In barium, there's 1 barium for every one of these, so that's the barium 2 plus. Same with the chromate. Oh, that's a 4.1, sorry. The chromate ion is also going to go down to 4.1 times 10 to the minus 6. So those two answers, that answers part I. And for part double I, it asks, why doesn't a precipitate form? So we're going to calculate the Q value, and the Q value on this reaction, right, so barium chromate is going to be BaCrO4 is in equilibrium with Ba2 plus chromate 2 minus. So the KSP would be the concentration of the barium times the concentration of the chromate, just plain old 1 to 1. So the Q value is going to be 4.1 times 10 to the minus 6 times 4.1 times 10 to the minus 6. This comes out to be 1.7 times 10 to the minus 11. And since this is smaller than K, no precipitate will form.